Hello everyone. Hope I'm audible. I'm Sai Venkatakrishnan, a PhD scholar in the Department of Computer Science and Engineering at IIT Madras. So we'll be conducting the live session for the NPTEL course Operating Systems Fundamentals. This is the week 12. The agenda of the live session would be as follows. We'll be discussing some questions pertaining to the week 12 lectures, and then we will be solving those questions, around 10 questions. So the main aim of this live session is to enable you to understand the lecture contents and also um, be able to solve any queries you have or in the lecture contents for week 12. You can either place your messages in the questions in the chat box, or you can unmute and speak. So let's get started in that case. The first question is the following: select the correct statement about indexed allocation. Is it option A, each of the files have its own index block of pointers to its data blocks? Or option B, can it be accomplished with a multi-level index method? Or option C, dynamic access is possible without external fragmentation? Or option D, all of the above? So which of the following four options are correct with respect to indexed allocation? Is it option A, B, C, or D? Any guesses? Which one of the following options would be correct? So the correct option is option D, all of the above. The reason being indexed allocation is, the way it works is, instead of directly maintaining uh, what blocks, so say this is your disk, right, the storage, and it's split into multiple blocks, right? So this is how your file contents are stored. So this is block 1, 2, 3, like that. So for a particular file, what all blocks are associated with a particular file, there are different ways of allocating that file in memory, sorry, in the disk. So one is contiguous. Okay. Let me use the different thing. So one is contiguous, that is, the contiguous blocks are all allocated to the same file. The second is you will be having a linked allocation, where say the first block, um, say block 1 is for file 1, block 2 might be for file 2, and the next block pertaining to file 1 would be stored as a pointer within this block 1. It will be pointing to some other block, say B20, and this will be also be with respect to file 1. So like that, it will be like a linked list sort of thing would be maintained. But if you want to do a random access or something, then you have to traverse the whole linked list and to find that particular block that you want to write or read from, right? That's the second way. And the third way is to maintain like an indexed allocation, so somewhat similar to the concept of page table, right? So you will be having like an index table, an index block, and the index will be storing like which one is for which block is actually storing the um, which block index is storing the first block. So this will be pointing to that b1, and some other block would be storing it for pointing to b5 as the next block. So this actually linked list, but instead of storing the pointers within the block, all those things are collected and separately stored in an index block for faster access and retrieval, right? But just maintaining, if you similar to how the disadvantage of a single level index block, single level page table, right? Single level index block, right? So say if you have a very large file, say of 5 GB or even say 20 GB or something, then those many indexes for each block you should be maintaining, right? So what should be the size of your index block? So to have uniformity and those things, like what we have seen in the single level page table, huge size for a single level page table we cannot be maintaining, because one is it will have high memory overheads, and also it's not like necessary always. Most of the processes or most of the files would be small in size, would not require that much of space. So maintaining such a huge page table for a small file is a complete like the index table for a small file is complete waste. So the same optimization what we did for the page table, the multi-level scheme, right, for the page table, indexing parts of the thing into the to do a page table walk and finding the virtual address to physical address. So in the same way, the index block will also be will be using a multi-level index. So the first few blocks would be pointing using that first level like that. So it will be like a multi-level index block will be used, similar to the concept of multi-level paging. So this is one. This is possible uh, in this indexing block. So uh, point A and point B is correct with respect to index allocation, and point C tells that a dynamic access is possible without external fragmentation. So in a contiguous, so what's external fragmentation in the first place, right? If you recall, when you have when you are trying to allocate some memory, and you can since it need not say you just have this 100 bytes only left, but you want so this is like 50 bytes over here free space, and this is 100 bytes, and in between some allocation is there. And suppose say your file 1 is already present over here, and if it's say like a contiguous allocation, it should always be contiguous. So uh, so you have to allocate some say in a linked list also, you have to allocate something together, right? It contiguous, the thing is you have to find that whole set of free space so that you can place the whole file in that contiguous allocation. But whereas in an indexed thing, it is possible to just take out that minimum size block if it's available, and place it in the index table pointing to that block. That's my next allocation like that. So this advantage to reduce external fragmentation is possible both in linked allocation as well as in indexed allocation. So so the first three options, all of them are true with respect to indexed allocation. So the option D, all of the above, is the correct answer. So any doubts in this question? Right, so dynamic access is possible. So the main thing what they tell is it possible to do an allocation without external fragmentation in indexed allocation? Yes, it is possible. So the what's external fragmentation in the first place? I have two free spaces. One is of 50 bytes, and yeah, the 100 bytes. Like so, I want to um, allocate that fully. I can just split it up into blocks, and since like it need not be contiguous in nature, right, the indexed allocation scheme will allow you to split up your blocks, and you can maintain distant blocks and just place it in your index table and point it to it. So it need not be contiguous in nature, so you can efficiently use up the free space. So that's what it means without external fragmentation. Does that answer your doubt? Like yes, it doesn't it's not like it doesn't need much space. So it of course needs space to maintain these index blocks and those things. That is the metadata over it, that is separate. The thing is if you want to allocate some block or something, some file, it need not be contiguous in nature, so that total space is split up, you can split it up and allocate it. So that's what external fragmentation is avoided, they mean by that statement. Right?
Yeah, we can ask, in external fragmentation, what I have studied that uh, basically, when we apply the blocks and there are separate space because, uh, you know, uh, there's space remaining like if there is a process like 60 bytes and we have a space remaining like 10 bytes but not contiguous, so we can't apply 60 byte process. That's the external fragmentation, right?
right, right,
So in index level, like we are, making the index. I mean, we are just why we are not having this external information because we are not. I mean, they are just kind of pointers.
yeah,
So
it's
they are,
just pointers and it need not be contiguous, so you can just split up your file and store it.
yeah. I mean, it's just like the same paging concept, and paging don't have external
Exactly
fragmentation.
the same paging concept.
Yeah. Okay, that's clear. Thank you.
Cool. Then let's move to question 2. Which of the following is correct about linked allocation? Is it that it locating a block can take many I/O cycles and the disk seek latency, or is it the case that each block contains a pointer to the next block, or is it the case that reliability issue arise when one of the pointer gets corrupted, or all of the above? So, which of the following statements is correct about linked allocation? Is it A, B, C, or D?
I think D because because if suppose if there is a link break between a linked list,
Right.
obviously it is corrected. We have to, I mean, we can't go through it.
Exactly. So
And
as yeah,
and the first thing is that locating a block can take many hours, obviously, because I suppose, I mean, it will be big on end. So we have to, in a worst case, we have to seek all the
right.
blocks.
Exactly. So the answer D is the correct is the correct answer. The option D. The reliability issue is because if the next pointer is corrupted, then you just lose track of your entire file. You should do some recovery scheme or something to get back your file contents and know where it is stored. And yes, the notion of linked allocation is like the next block pointer is stored in the current block, the previous one. And locating a block as in a random access will take many IOs because you have to traverse the whole linked allocation, the linked list. Right. So option D is the correct answer. In that case, let's move to the third question. So this is a numerical one. Assume that there are 200 cylinders, 0 to 199, and if the initial position of the read write head is at cylinder 39. So this is your initial position, and calculate the total head movement following the C look policy for the read request sequence coming in this order. So this is your initial thing, and this is your sequence 25, 1112, 84, 188, 2 comma 154, right? So now we should calculate the head movement. So C look policy is uh, assume it's going in it should go in one direction only, and while coming in there is no like reverse direction it will read. It will again come back to the starting and again go from start to the end in the same direction. It will be going again and again, so it don't reverse and again traverse. It won't go like this. Instead it will just go like this and again like this, right? So this is not there, so this is
Yeah,
one.
it's like zigzag motion. I mean,
Sorry.
it's not like zigzag motion. It's going in a one direction only.
Yeah, exactly. It's not like the scan mode. The other one is scan. It will be going in like it will be reversing when it reaches the end. Each end it will be reversing, but see, look, it will just be going from one direction to the other. That's it. And the thing between C look versus a normal uh, okay, C look versus okay look, right? C look versus look, yeah. So the thing between C look and normal look is no, no. Look, look and, yeah, right. So C look and look is it will not be going till the end of the disk. Instead, The last request, whatever it's there, it will just read till that point and again come back. Right, so that's what C loop does. Okay, so to calculate the total head movement, the initial position is at 39. So from 39, whatever is the nearest thing. So from 39, assume it's going from left to right, like increasing numbers, right? So from 39, the first one would be 84, and from 84, the next one coming is
One.
112, and then 154, then 188, and again it comes from first. So 2 will be the fifth one, and the final one would be 25. So now to calculate the head movement, the number of cylinders it should the disc it traverses, right? So 84 minus 39 plus 112 minus 84 plus 154 minus 112 plus 188 minus 154 and plus 188 154, and now it will come back to 2. It won't go till 199, not till the end of all cylinders, but just what the last request was at that time. So now it will just come back to the starting request 188 minus 2 plus finally it will go to 25. So just adding up all this, you will get, let me just 84 minus 39 telephone 45 plus 28 plus 30 42 188 154 34 plus 186 plus 22. Okay, so this is what thing is. Let's see calculator.
You lost my screen and your screen is not visible.
Sorry,
Your screen is not visible actually. I'm.
now is it visible?
Yeah.
Okay. 45 28 42 45 plus 28 plus 42 plus 34 186 122 34 186 plus 22 358, right? So 358 is the correct answer.
So
So
we are basically uh, taking consideration of only quantity, right? I mean, not the sign. I mean, there is no positive motion or negative motion. We just need to
no,
check that.
no, so any direction, it's just the we are calculating the number of times it's moving, right? The number of
Okay.
steps it's moving, so that is always positive only.
Okay.
It's
I mean, this is a C look.
direction. No, direction doesn't count in this thing.
So this is a C look. I mean, if we consider the normal axis,
So if it's a normal look means the thing between C look and normal look is either it will go till the end, that is 199, or it will just go till the last request 188, right? That's the difference.
can you explain the calculations as well?
Explain the.
Calculations as well for the normal one.
So for the normal look, one second. So in a normal look, what happens is th- this thing till here it would be the same, okay, just like that. But now it will go till the end of the disk, till 199 it will go, right? 199 minus 188, right? And then it will come back all the way till the start, 199 minus right. So this is what happens in the look algorithm.
So basically, there are two, lookups like C scan and normal lookup. Is
Right.
there any?
So scan is
Yeah.
there, C scan, and then look, and then C look. These are the four different things, and also the first thing is the other thing is first come first serve, and afterwards shortest seeking time first, similar to that shortest job in the scheduling.
First come first service, like
Yeah, we
whatever.
should find the order in which they came, and we should just execute this. I'll explain with the same sequence 20, 25, 1112 and 184, and say your initial head is at 39. Okay. In a scan, what it will do is it will start at 39. Okay. So first it will service 112 and then 184, and then it will go in the opposite, that is 25 and then 2. Okay. In C scan it will okay, so and say it is the same, like total number of cylinders is 0 to 199. So here actually before going to 25 it will go till 199, and then only come back to 25. It will reach the end and come back to
In
120, come back to
in C
25.
scan.
Okay.
In C scan.
uh, that is scan. In C scan, what happens is the same way, but 112, 184, 199. But instead of going till 25, sorry, reversing and reaching 25, it will again start from first. That is 0 and then 2 and then 25. Right. So actually, scan and C scan is different. Right. The difference between scan and look is it will the reversing the direction, that is all the same, only whether it goes till the end of the disk or not. So in my previous explanation I reversed actually C scan and look. That was not the case. Actually scan and look, its working is same, except it doesn't go till the end for look. C scan and C look also the same thing, it doesn't go till the end. Difference between C scan and scan is whether it reverses the direction or not.
Okay.
Right.
Thank you.
Yeah. So so using this trick you can do, and in that case let's move to fourth question. So we have the same thing. Find the calculate the total head movement following the SSTF policy. Right, shortest seek time. So seek time as in the number of head movements you should do, the number of cylinders your disk head should move to reach that specific to service that request from that cylinder. That is the seek latency. Right? So the shortest seek time first is, say they have given it's 39, the initial head. So you're having the current request, the request queue is filled up in this way. So from 39, whatever is the nearest one, right? From 39, what, assuming like all these are already present in your request queue and everything has filled up simultaneously, right? So at this time, from 39, whatever is the nearest.
84.
So 25. From 25, whichever is nearest, that is 2, right? From 25, the shortest seek time is 2, right? And from 2, we will have 112, sorry, not 112,
84. 84.
84. And from 84, we will have 112 and then 154 and then 188. So if you just calculate the same way, 39 minus 25, okay, that is 14, and then it goes to 2, right? 25 minus 2, 23, and then 84 minus 2, which is 82, and then 1112 minus 84, which is 28, and then 154 minus 1112, which is 42, and then 188 minus 154, which is 34, and adding it 4 3 7 2 9 9 8 17 2 19 4 23 2 1 3 3 2 5 5 8 13 13 6 19 3 19 plus 3 2 2. So 223 is the correct answer. So this is what is the case in shortest seek time first. Any doubts in this question?
No.
Right. So in that case, let's move to question 5. Which of the following disk scheduling algorithm searches in only one direction and the arm goes only as far as the last request before reversing its direction? So based on that thing, right? Well, the previous question, what we have discussed, searches in only one direction means the C prefix is there, and arm goes only as far as the last request before reversing its direction. This means look. So it's
Yeah.
C look. It's option B is the correct answer. If the searching in one direction, if it's not present, then the C thing is not, so it will just be look. So using that hint, you can easily find this question, the answer. So any doubts in this question?
No.
Right. Good. So let's move to question 6 then. Which of the following disk scheduling algorithms should not be picked for systems that place heavy load on the disk? Is it scan, C scan, or shortest seek time first? Or all of the above?
Look, all of the above can't be options. Uh, I think the answer should be between B and C. Uh,
Right. So the correct answer is option C, shortest seek time first, because in scan and C scan it just tries to be uniform, as in it
yeah.
goes in one direction or like a reverse direction, right? Servicing in that direction and then coming in the reverse. So there is not much of uh, some
Different.
priority given to someone like that. Whereas in SSTF, what happens is shortest seek time first. All the short jobs are all prioritized, right? So what this means is, say I have a long pending input file which is to be read or something, then say in between some other huge number of small requests are still there, so that long pending IO request would be starved, and assume that these short short requests are coming in like in a long queue, and it is always coming up, right? So in that case, just blindly following the shortest seek time first or something, right? The way in, so the shortest seek time is like not exactly short job, sorry. So it is like the distance covered is should be small, right? So at that time, say your current head is at 39, and then you have 25, and and you have say 50, right? So which one is the nearest to travel? So if you want to go to 25, it is 14 places you should move, and this one is 11. So you will prioritize this only, and in a similar way, the seek time. So whatever is one part of the disk alone, say your um, say out of the 0 to 199 cylinders, one say request 1 is for the cylinder 1 C1, and other requests is request 2 till request 100 are somewhere in the range say 100 to 199. Okay, between this range the other requests are all there, and your initial head was at 150, assume this. Then what happens is before it goes and uh, services this request 1 which is at cylinder 1, since based on the shortest seek time it will just go and finish all these first in this cluster, and then only it will move to request 1, provided no other new request comes which is nearer to it than the starting request pointing to cylinder 1. So basically there is a possible of starvation.
Here we are asking for heavy load on the disk.
So heavy load as in it is in a heavy load what happens, right? All the requests would be towards one part of the disk like that.
So this is applicable for the example you shared, because if all the accesses are going to particular cylinder, then obviously it will going to have more load.
Yes. So it should not be picked for a system that places heavy load in the disk. Like so, heavy
But
load has been
can't we
say.
have the same scenario in C scan? Like,
So in CSCAN you cannot have the same scenario, right? Say if it starts from 150, it will just go in this direction, finish the request, and CSCAN is it will again come back from the start. So after some point, you know for sure that C1 would be C1 would be for sure serviced. Whereas for shortest seek time, you cannot
I mean
argue.
that depends the kind of blocks we are going to access, because suppose if all the blocks
Yeah, yeah,
from 199,
yeah. So
then CScan and SSTF are going to act like same. I mean load wise.
yeah, yeah. So exactly. So the scheduling algorithms depends on the request queue and all those things. But generally, if you just look the intuitive policy of CSCAN and SSTF, CSCAN is just like it gives uniform priority to all the things, right? From the start to end, I will just service, and again from start to end. Whereas in SSTF, as and when the requests are coming, what's the nearest request it can go and service? That's what it sees. That's like that will lead to starvation. That's what they mentioned. So in
Okay,
a heavy load on disk, it might lead to starvation, and that particular service might not that request might not be serviced at all after a long time, even if it came in the starting or something.
okay,
So the other things, then you should try to bring in like that waiting time or something, and try to do some priority and those things all. Right? But then in that case, your disk latency itself is very high. It will take around 300 cycles or something, like more than that, to go and fetch from your disk and store it in memory, and your process would be waiting for. So now if you do all these scheduling things and all sort of complicated things, right, then it will increase the waiting time only. So
okay,
that's one reason why they went for like a simple algorithm, but an effective one, just C scan or scan.
okay.
Right. So option C is the correct answer. In that case, let's move to seventh question. In the open file locking system, the advisory access policy is allows the access request ignoring the lock status, or it denies the access request depending on the lock held and requested, or it is the processes look up the status of lock and decide what to do, or option D, none of the above. Which one of the following is the correct answer? So open file locking system, as in when a file is open, if it's for a read operation, then not required. Multiple processes can go and read, right? So that file handler can it can be given. But if it's for a write operation, then writes should be exclusive, right? Because otherwise it might corrupt the file. So in that case, the write lock should be an exclusive lock. So in that case, the open file locking system should consider these aspects. So two policies are there. One is advisory access policy, and the other is mandatory. So which one of the following options corresponds to advisory access policy? Is it A, B, C, or D?
Is it C?
Exactly. So the correct answer is option C, as you had mentioned, Sashikant. So the advisory access policy is not executed by the OS or the storage drivers, the storage management system in the OS. Instead, it just returns the status of the lock, and it's up to the process to decide whether to go ahead and do something, and to decide to acquire the file handler and provide for the read and write operation or not. So it's up to the discretion of the process. In a mandatory access policy, it is the OS has to take a decision whether the request is denied or permitted. So it's just the policy enforcement, whether it's mandatory or advisory. So that's what it's all about. So if no doubts in this question, then let's move to 8th question. In the sequential access method of looking up files, the file pointer is affected by the read next or the write next command. So how it is affected? Is it incremented to the next value or reduced to previous value or reset to 0? It's an easy question actually. Any guess which one is the correct option?
I'm going to say A because
Yeah,
pointer.
reset into. Yeah, so it's just a next value. So option A is the correct answer. So let's move to question 9 then. Which of the following directory organization use links? Links are used to point to both files and subdirectories. Is it general graph directory, acyclic graph directory, or tree structured, or none of the above? Which of the following directory organization links?
C.
The
It's
links
C.
are used. Sorry,
C. Tree structure directory.
B. C you are telling, is it?
Yeah.
Okay, C is not the correct answer, Sachikant. The correct answer is B. The thing is, in the main use of these links, right, is for maintaining these shared files and directories. So this is what links are mainly used for. Say this is one shared file SF1, and the shared file it should be accessible from say this is directory 1 and this is directory 2, right? So this is what I will be having a link over here, and this link, the type um, for the link will have its own type, and when you look into this link, it will store the actual file which it points to. That is this shared file 1. And say if the user goes to directory 1 and looks up this link, it will be the same file. If he goes to directory 2, it will be the same file. So say like this directory owner is user 1, and this directory's owner is user 2, and you want to share some file between them, right? So in that case, the links will be used. And in set
But
of nodes, if you have this links in between, right? So this is
what
basically,
is the, what is the difference between acyclic graph directory and tree structure directory? Because I mean, if you consider the Linux node system, inodes. Is it not a tree structure? I mean,
It's not tree
trees have
structure.
cycles,
It's I guess acyclic graph because the tree structure is the it's based on a tree data structure itself, right? One parent node only, right?
I mean,
So
tree also don't have cycle. A cyclic graph directly should be like a graph which have no cycle, right?
right. So you don't have cycles in the acyclic graph, right? You don't have a cycle in this case.
Tree is also a graph with no cycle. I mean,
A
in tree
tree,
we have cycles.
no.
But what a difference? I mean, I'm not getting it because tree structure is itself a graph, a cyclic graph example.
Tree structure does not. Okay. No, the difference is the tree structure directly does not allow for the shared file concept at all, right? It's just like it does not have the concept of shared files. It does not allow, say, the same file and for distinct, right? The same directory 1 and directory 2 to point to this same thing. This is not allowed in a tree structured directory. So this is where the acyclic graph directories come in, and they change this thing like to a specific link type actually.